Hi everyone, welcome back. We spent the last 2 weeks putting in a lot of work to come up with all of our different derivative rules. And now that we've done that, we're going to use them to do 4 different things tonight that are not necessarily related to each other at all. So you shouldn't expect a progression from one topic to the next. Our first topic is called implicit differentiation. So sometimes we'll be given a curve where it is difficult or even impossible to write y explicitly in terms of x, and yet we should still be able to find the slope of that curve at various points. So the question is, what do we do when that happens? So for example, let's consider this curve. X cubed plus y cubed equals 9/2 xy. That generates this beautiful curve, which has a name. It is called the folium of Descartes. That's the same Descartes that you met in philosophy class, the same one after whom the Cartesian plane is named. So here we could, in theory, solve for y in terms of x, because this is a cubic equation, and every cubic equation is solvable. So I will invite any of you watching at home who know how to solve cubic equations to go ahead and do that. Nowadays, very few people know how to solve cubic equations. In fact, there's never been a time when many people knew how to solve cubic equations, although it used to be an actual sport. People would sit up on a stage and try to compete a few hundred years ago to be the first one to solve a cubic equation. But now we have different things to entertain ourselves. So we could solve this for y if we were really good, but we're not that good, and that's okay. It would be a big mess to solve it for y. But there is a way to do it, just like there's a quadratic formula. In fact, there's a way to solve a 4th degree. There is no way to solve a 5th degree, it turns out. You can actually prove that. So you can do it 2nd degree, 3rd degree, 4th degree, and then beyond that, you're stuck. There is no general way to solve those equations. Nevertheless, I think you would agree that at almost any point on this curve, I should be able to draw a tangent line, maybe except at the origin where there's 2 different tangent lines, we might run into some trouble. So what can we do? We don't even bother now to try to solve for y in terms of x. We just leave it the way it is if we want to find dy dx. So we just take this equation, and we'll take the derivative of each side, just as we've done a few times before. With x cubed, there's nothing unusual happening. Its derivative is just 3x squared. Now what happens with y cubed? If we had been able to solve for y in terms of x, we would now have some formula for y in terms of x. It might be as long as your arm, all being cubed. So you can think about this as representing some function y of x all being cubed. And by writing it that way, it should suggest to you what rule we need to use to take the derivative of y cubed. What rule are you thinking of that we'll need to use here? We've got one function inside of another, so I hope that makes you think that we need to use the chain rule. So we've got something cubed. So the derivative of something cubed, we know, is 3 times that same something squared. But then the chain rule says we're supposed to take the derivative of that inside function. So we need to say, what is the derivative of y? And now it's up to you. You could write y prime. Sometimes these equations get pretty messy, and you've got a lot of y's and y primes around. Some of them might get mixed up. So I'm not going to write y prime. I'm going to write dy dx. So that came from the chain rule. Now I know somebody has a question about why this dy dx is here. Let's remind ourselves of the very last problem we did last week. I intentionally chose to name that function y instead of f of x, like we did in the previous example. We had y equals this. We decided we need to do logarithmic differentiation, remember. That's not the relevant point here. We had ln of y, it became this. And then we took the derivative of each side. And when we took the derivative of ln of y, we didn't write only 1 over y, because we recognized that this y was standing in for this whole formula. And therefore, it was really one function inside of another, and therefore we needed the chain rule. So the derivative ln of y was 1 over y, then dy dx. That's the very same thing that we're doing here with the y cubed. We're thinking about this as being some formula with x's in it, maybe a lot of x's, all being cubed. We don't happen to know what the formula is, but that doesn't bother us. We know its derivative's name is dy dx. So that's where the dy dx comes from. If you had felt like it, what could you have put here? You could have said x is standing for x, and then you could have put dx over dx, but that's just saying the derivative of x, which is 1. So typically we don't bother to write dx over dx, but you're welcome to if it makes you feel more comfortable in writing the dy over dx. Now we have to take the derivative of the other side. What rule are we going to need on that side? I think we're going to need the product rule. So if we rewrite this as, say, 9/2 x times y, what's the derivative of 9/2 x? That's just 9/2. And the product rule says we multiply that by y. Then we leave the 9/2 x alone. And we take the derivative of y. And again, the derivative of y goes by a variety of names. You could write y prime. But we're going to write dy dx here so that we don't get our y's and y primes mixed up. So we've managed to take the derivative of each side. So are we done now? We're not quite done because what we're supposed to be doing is solving for dy dx. So now this has turned into an algebra problem. We've got two different dy dx's. So what should our strategy be from algebra class? We want to get all the dy dx's on one side, right? So let's get them on the left here. So 3y squared dy dx. Let's keep that on the left side. We're going to move the 3x squared to the other side. We'll move this 9/2 x to this side, 9/2 x dy dx. We'll keep the 9/2 y on the right side. And we'll move the 3x squared over here. So now we've succeeded in getting all of our dy dx's on one side. So the next step would be we don't really like to have two dy dx's. We'd like to have just a single one. And we can accomplish that by factoring. So we can write dy dx times 3y squared minus 9/2 x equals 9/2 y minus 3x squared. And now we're almost done. All we have to do is divide to get a formula for dy dx. So there's our derivative. Dy dx equals 9/2 y minus 3x squared over 3y squared minus 9/2 x. And to me, that looks very visually pleasing. It's got some nice symmetry in it, and that symmetry comes from the very nice symmetry in this original graph. Incidentally, why is it called folium? Folium comes from a Latin word that gives us, in New England, us New Englanders, something that people tend to like to do here, go around and look at leaves in the wintertime, or in the autumn, and we call that foliage. So this is like a leaf. That's why it's called the folium of Descartes. One thing to notice is this a function? No. This does not pass the vertical line test. For example, if x equals 1 here, trust me, that x equals 1 is around here, we have 3 different y values on this graph. So if you only knew the x value, would you expect to be able to say what the slope is? No. There are 3 different slopes at x equals 1, right? There's whatever this positive slope is, this positive slope, and this negative slope. And we can see that in this formula for dy dx. How does this formula look different than all of the other dy dx's we computed over the last several weeks? It's got x's and y's in it. So just knowing the x value wouldn't be enough. We would need to know the x value and the y value, and then that will tell us what the slope is at any given point. So in fact, the next part B to this question, which is on the next board, is going to be to say, what is the equation of this tangent line at this point 1, 2? So of the 3 different places where x equals 1, one of them happens to fall nice and cleanly at 1, 2. Do you believe me that 1, 2 is even on this graph? How do we know? How would we check if 1, 2 was truly a point on this graph? We would have to plug it in to make sure we get an equality here. So let's just verify this. If I plug in 1, 1 cubed is 1, plus 2 cubed is 9. So I got 9 on this side. And on this side, I got 9/2 times 1 times 2, so I get 9 on that side. So that proves that 1, 2 really is on this curve. But for example, if you were to try to plug in 1, 3, some point up here, both sides wouldn't equal, which is how we know 1, 3 isn't on this curve. So now we're going to try to find the equation of this tangent line. In the spirit of trying to think in advance of what a reasonable answer would be, what kind of value to expect to get for the slope. I hope you said you expect to get a positive value because we've got a positive slope. That's for m. And for b, we also expect to get a positive number because we're crossing the y-axis at some positive value. So let's do that. So part B, find the equation of the tangent line at the point 1, 2 that we just wrote up there. So first we need to find the slope, m, which is dy dx. It's been a while since we used this, but remember this back in week 4 for evaluating Leibniz notation? Dy dx evaluated at 1, 2. That's how we would write this formally. That vertical line we said back in week 4 means evaluated at. So I'm going to plug 1 comma 2 into my formula for dy dx. So that's 9/2 times y, which is the 2, minus 3 times x squared, all over 3 times y squared minus 9/2 times x. And I think this will simplify pretty well. 9/2 times 2 is just 9, minus 3. We get a 6 on the top. On the bottom, we have 3 times 2 squared, which is 12, minus 9/2. 12 is 24 halves. 24 halves minus 9 halves is 15 halves. And then dividing by a fraction, we multiply by the reciprocal. We get 12 over 15, which we can simplify to 4/5. So what have we figured out? So we know y equals 4/5 x plus b. 4/5 is a positive number, just like we were expecting to get. And now it's up to us to find b. So let's plug in to make that happen. We know that the y value we're going through is y equals 2, and the x value is x equals 1. So I think we get 6/5 for b when we do the subtraction there. So the equation that we're looking for, the equation of that tangent line, is y equals 4/5 x plus 6/5. And in fact, this formula that we found for dy dx in part A will allow us to find the equation of the tangent line at any point except at the origin, whereas we noted there are 2 different tangent lines. One is 0, has a slope of 0, and the other was vertical, so it's not even a function. It's just the line y equals 0. X equals 0 is a vertical line. Yes, the line x equals 0. We have an applet for this that you can play around with to drag the point around and see how the slope changes and see if that agrees with the dy dx that we found. And so go ahead and do that. We'll come back and do one more example of a different curve.